Team Realisk presents a methodology for monocular depth estimation using transfer learning implemented as a part of the 2021 IEEE RAS Winter School on SLAM in Deformable Environments from the date 5th July to 9th July 2021. This competition was organized by the University of Technology, Sydney. The aim was to promote research on robot localization, mapping and navigation in deformable environments. All the equipment, datasets and tools required for the competition were provided by the organizing committee. As a part of the group project, we have successfully implemented the following: building the deep learning network, improving the loss function, adding data augmentation, and designing a new encoder and decoder network. Depth estimation using vision sensors is usually done using stereo cameras so that the two cameras can be used to triangulate the position of a certain point in the environment. Stereo cameras utilize two cameras to triangulate the distance of certain point in environment. A depth map is an image containing information of distance of points in the environment from the camera point of view. In this project we focus on the monocular depth estimation problem and its potential applications in deformable simultaneous localization and mapping. Using monocular camera offers benefits like low power consumption, lightweight and low cost. Moreover, monocular cameras can also be used for estimating the depth using various monocular cues like defocus, texture variations and gradients, cold/haze, etc. We estimate the dense depth map of each pixel using a single monocular RGB image using a deep learning-based transfer learning approach. Additionally, we implement a transfer learning-based method and an encoder-decoder structure to solve the monocular depth estimation task. The NYU dataset V2 is used for training the depth estimation models. In depth regression problems, a loss function is defined as a function of difference between the ground truth depth map and the prediction of depth regression network. To train our network, we incorporate different loss functions and compare them on an individual basis as well as their weighted sums. We attempt to find a combination and subsequently a loss function which minimizes the difference of depth values while also penalizing distortions of high-frequency details in the image domain of the depth map. The loss functions implemented are as follows: 1. Pointwise L1 loss 2. Lgrad loss 3. Lsim loss 4. Burhu loss. An inherent problem with such loss terms is that they tend to be larger when the ground truth depth values are bigger. In order to compensate for this issue, we consider the reciprocal of the depth. Data augmentation is the process through which individual samples in the dataset are manipulated while preserving their innate characteristics, which leads to a better generalization, thereby reducing overfitting. The original images are shown on the right whereas the transformed images are shown on the right. Due to lack of suitable processing capabilities, we trained the model using only 1000 RGB images. Moreover, we trained the model on just 20 epochs for faster computation and timely completion of the project. In this project, we have implemented DenseNet 169 that is taken as a baseline for validating the performance of two modified encoder-decoder architectures. The NYU dataset V2 is used for training the above-mentioned depth estimation models. Using an extensive analysis of different loss functions and data augmentation techniques, the performance of the three models were compared. It was observed that DenseNet 169 outperformed the custom encoder-decoder architectures. Moreover, the weighted sum of the loss functions decreased the model loss. Lastly, by incorporating various data augmentation techniques, a significant amount of variance was brought into the dataset that subsequently helped in enhancing the overall performance of the model. Monocular depth estimation is a useful tool in multiple fields where there are constraints on hardware size, cost and power consumption. A significant application of this work is in space-constrained dynamically deformable environments in the human body for functions like endoscopy or colonoscopy. Additionally, it can be a useful tool in the search and rescue operations for examination while navigating through small cracks for an extended duration of time. This method for depth estimation can be improved upon in the future by devising new and better loss functions. Additionally, an improvised weighted combination of the same or better loss functions can be devised to get a better estimate of the depth.